Okay, so this is Physics 1C for February 23rd. Last time we talked about electric fields, and we're going to keep talking about them today. I just want to briefly remind you of kind of the one big thing that we came to at the end of class last time. We talked about the electric field created by a point charge, and to remind you what that is, the idea is that if you have some kind of a charge, let's say you have a charged particle that carries a charge that you call Q, and let's just say that it's positive. If you go to some point that is a distance r away from the charge, then we found that you can define something called the electric field at that location. It's a vector, and for a positive charge, it points away from the charge. For a negative charge, it points towards the charge. And the value of that vector, the magnitude, is given by the electric constant k that we talked about last time, which is something like 9 times 10 to the 9, multiplied by the size of the charge, and then you divide by the distance between the charge and the point. And we call that the electric field of a point charge. And by comparison, if you were to have a negative charge, like let's say over here you have some kind of a negative charge, negative Q, if you go some distance away from that, you can say the same thing. It just, you define the distance you are away from the charge to be r, and you come to some point right here, then we say that for a negative charge, the electric field points towards it, like this. But has the exact same value, just you take k times q, you divide by r squared, you just make the vector point towards the charge. So this problem is a problem where we can kind of test and try to understand what we learned last time. We're going to do 2 problems that involve point charges, so you can get some like decent exposure to how to do these type of problems. Okay, so I'm just going to go to each of these points here, and we're going to go through and solve. The first 2 are pretty easy. The last one's a little more challenging, but not super challenging. Okay, so if we start at point A right here, we're told that you have 2 charges. One is positive 12 nanocoulombs. The other one's negative 12 nanocoulombs. And the distance between them is 0.1 meters or 10 centimeters. And then you have some other distances that are marked off here. We want to compute the field caused by Q1, the field caused by Q2, and the total field basically at each of these points. So I guess there's 9 answers, right? We need the field caused by Q1 at point A, the field caused by Q2 at point A, and then so on and so forth from there. Okay? So, and I can't see, there we go. Okay, so let's start at point A right here. And let's first find the electric field caused by the positive charge. These are labeled Q1 and Q2. So I'll label the fields as, I guess, E1 and E2. So at point A, E1, first of all, we've got to figure out direction. That's usually what you need to do first. So for the positive charge, what's the direction of the electric field at point A?
Towards the right.
That's right. Okay, so let's draw a little vector on here to represent that. And I'll just label it as E1. Now, while we're doing that, we might as well label the same thing for Q2. We'll use black for that. So what's the... Actually, it's blue, because the charge is blue. Okay, so what's the direction at point A, so at this location, of the electric field created by Q2? Does it go left or right?
Also towards the right.
So they go to the same direction, exactly. Okay. Now, which one's going to be bigger? The field caused by Q1 or the field caused by Q2?
Q2.
Yeah, because it's closer, right? Okay, so we would have a larger vector for that one. Okay, so now let's go through and calculate what these are. We've got our general equation right here that says you just take k times the charge, you divide by the distance, where the distance is the distance from the charge to the point. So here we're doing point A, so our distance is just the distance from the charge out to point A, which is 6 centimeters, right? So let's plug all those into an equation. So we've got k, the value of k is 9 times 10 to the 9, and then it has these units. We multiply by the size of the charge. Q1 is 12 nanocoulombs, so nano is times 10 to the negative 9. So we throw that in there. And then we just divide this. So from A to Q1 is 6 centimeters. We put 0.06 meters down here. And then we square it. Now, I want you to calculate what this is and type an answer in chat. And then I'm going to start writing down what E2 is. And you guys do the same thing for that one. only thing that changes here for this one, it's a negative charge, but we've already taken care of the fact that it's negative by drawing our vector to the right. And it looks like the answer to the first part is 30,000. Okay, thanks. Newtons per Coulomb. Oh, and then one other thing here is this is squared. And then so what do you get for this one then? This one should be bigger. How much bigger? $67,500? Yeah, that's what I get to. Okay. So, there's our two values. Now, the electric field is it's a vector technically, right? So really, if we want to write these values properly, what we would say is E1 would be equal to 30,000, maybe I hat, for pointing to the right, newtons per coulomb, and then E2 as a vector will be written as 67,500 newtons per coulomb. You could write it in, obviously, and then this is also going to be I hat. And then we also were supposed to find the total fields, right? And then we can sum these two together, basically, add them up, and we get that the electric field's total at point A is going to be equal to the sum of these two, so what was it, 97,500. And it also points to the right. So that's the electric field at that location, point A. You don't have any questions? Okay, let's continue on to point B. I think what we'll do is there's not a lot of room here, but I don't want to completely erase all the work we did. So let's just shift this over here a little bit. Maybe make it a little bit smaller so you can still read it. And then we'll proceed to do point B. So at point B, let's start with the positive charge. Can you just tell me in the chat, what direction does the electric field point at B for the positive charge? At point B, what's the direction of what we call E1, maybe? Left, that's right.
Left.
Because it always points away from the charge. So here we go. Get a vector that goes out to the left like that. Call that one E1. And then what's the direction of the electric field for charge 2?
Right.
So, yeah. Let's make that one blue. Okay, so we got the directions. In this case, it's going to be E1 that's bigger, right? Because we're closer. Anytime you're closer, it's going to be a bigger value. They're both exactly the same distance away, though. Oh, no, sorry, not the same distance. My bad. Okay, so let's go through and calculate these. So E1. Now, if you've already calculated it, you can put the answers in the chat if you want to. I'm not going to keep writing K. Hopefully by now you know what K is. It's written right there. So we do K multiplied by the charge, which is 12 nanocoulombs. And we divide by the distance, which is 0.04. And I'm also going to multiply. We'll just do this all in one step. I'm also going to multiply by negative I hat right here, because it points to the left. And I think this calculation should be the same as that calculation right there. So this should be negative 67500 newtons per coulomb times I hat. And then we do the blue one. Now, it's really your choice how you decide to put these negative signs in here. I mean, you see in the first part up here that it was a positive charge, but it gave you a negative answer. So I know you might be really tempted to put a negative sign in here, and you can do that if you want to. But I think it's better to just draw the direction, personally. It's really up to you. Okay, so this is a distance of 10 centimeters plus, so 0.14 meters. And that's going to be also multiplied by positive I hat. Okay, so we haven't done this calculation yet. Someone calculate what that is. It's going to be 12 times... See if you can type...
5,510.
Okay. Yep, I got the same thing. So 5510, this is positive. And look, it's so much smaller. And this is because, of course, the electric field falls off really fast. R squared, inverse square law means if you get too far away, you stop feeling the effects of those charges. We're looking at that's like an order of magnitude, right? Like almost 10 times as much. In physics, we say order of magnitude. I think in most of science, when we mean a power of 10. So, yeah, it's quite a bit bigger, even though it's 14 centimeters versus 4 centimeters. Okay, so we know those two values. We also want to find the total electric field there. So we sum those up. So we just add them together. And what we end up getting is that the electric field at point B is going to be equal to the sum of those two. Now, I'm going to keep the value I have in my calculator here. So I didn't round anything off. So you might get something a little bit different. But to a few... Here, let's write this in scientific notation because it's kind of... I'm sure we'll all get different answers. I'm just going to write 6.20 times 10 to the 4. Oops. Do you all agree with that answer?
Yeah.
Okay. All right, let's smooth these over. Here, we can probably finish the rest of this problem down here, actually. Can we, though? No, we kind of need the whole picture for this last part, because we're going to do some trick now. All right, we'll just move all this stuff over here. The same thing as before, we'll just make it smaller. I'll put it right there. You are over here. Okay, so the last part is part C. I think I'm going to move this down a little bit so we have some room to draw on the picture and maybe make it a little bigger. No, I just realized doing that. Okay, we don't need these other ones though, right? You guys understand what was happening at the bottom, right? I mean, I can still line it back up. Maybe it helps to see it. Okay, so now at point C, we want to do the same process. So what's the direction at point C for the electric field created by the positive charge Q1?
Radially away.
Radially away, exactly. That's the right way to think about it. Always, if you go along a line of, it's like a radius, it's always going to point away. Okay, so you draw a line like that, and we'll just make it that long. That's probably fine. Okay, what about, I just want to see real quick here. If I shift this to here, if it actually, yeah, it looks like it lines up. Okay, so what about Q2? What direction is that one point? The electric field due to Q2.
Radially towards.
Yeah, it's negative, so it goes toward it. So get another shape and make it blue. Straight line. Now, how long should this one be? Should it be longer? Should it be shorter? Should it be the
same distance?
Same thing. Yeah, exactly. Something like that. I don't know if they're the same length, but I'm just going to draw another line here to test if they are. Oops. It's pretty close. Okay, so those are our two vectors. Why won't it delete it? Delete. Okay, so those are our two vectors. The bottom one's E2. Okay, and now we need to do a little bit more, a little bit of trick, because we can't just add these two vectors as simply as we did in these two parts, because the vectors are at angles, so we have to go back and use components or something like that. So if we look at these two vectors, one thing we notice pretty quickly is that if we break them into components, we're going to have, in both cases, there's going to be one component, I'll try to draw this relatively straight, that's going to point up like this. So each one of them is going to have a y component that points like this. And because they have exactly the same length, we know that these two vectors are basically going to add to 0, right? So at the end of the day, we really just need to find the x components of these vectors. The component that points parallel to the x-axis like this here. So we'll call those, the normal kind of thing we do is we just put a little x subscript down here for this, and we put a x subscript down here for this. I know seeing a lot of x subscripts can be kind of overwhelming, but it's a short way to notate information. And in this case, what we're notating is that this is the x component of that vector. Not that one, but this one. And that's why we need to use this kind of notation. So you need to get used to it, because we're going to do trickier things as we go along. Okay, so we just need to find that component right there. And in order to do that, we also need to know something about an angle probably. There's other ways we could do it, but if we knew, for example, what this angle right here is, it should be the same as this one. And we should be able to use that to figure out what this component down here is equal to. Just like you do with forces, right? You break everything up into x and y components, and you add the components together. So what we know is that the electric field at point B, oh, this is point C, isn't it? Is going to end up being equal to the sum of what E1x is plus E2x. And we also know that the values of those will just be equal to whatever E1 is multiplied by, see how well you guys remember this stuff, what trig function do I need to write here to get E1x?
The cosine.
Okay, you said
Oh,
cosine and then someone said sine.
Oh, wait, no.
What's it going to be?
Well, theta, it will be the sine.
Yep, exactly. Okay, so we put sine theta right here. And if you don't remember, the idea is that if it's opposite, and this is written a little bit weirdly here, this is E1. Right? So hypotenuse, this is the opposite side. So that means we use the sine. Okay, so E1 sine theta plus E2 sine theta. Okay, so we can actually just factor that out. A lot of these, actually, if you think about it, we already said E1 and E2 are equal to each other, right? So really all we need to do is to solve for one of them. And then just double it, really, right? So we'll just write this as 2 times E1 sine theta. And what's that equal to? Well, it's going to be 2 times E1, and E1 is going to be K times the charge, which was 12 nanocoulombs. I wonder if you all would be okay if I actually just wrote nano in here, and then you just convert it on your own. Because I feel like writing the scientific notation, not only does it take long, but I think it conveys less information. I don't know. Anyway, we're dividing by the distance. In this case, it's 0.13 now. I don't know if you could tell, but that's a special triangle that's created inside of there, right?
Mm-hmm.
If you cut the distance in half on the bottom, you're going to get a 5, 12, 13 triangle. Okay, so does anyone know what the angles of 5, 12, 13 triangle are? That doesn't really help us because we still need to know the angle that shows up right here. And to do that, we'll just do a little bit of trig. It's really easy.
I mean,
What's up?
you could just, if it's a right, we could just use the side lengths.
We could. Yep, definitely. Okay, so this is a side that's going to be 5. If we drop, basically I'm saying you drop a perpendicular on here. Our angle is theta, and this is 13. So, and this is going to be, well, I'm just telling you, it'll be 12, but we'll use the numbers that are actually on the picture. So we need theta, and theta is just going to be equal to, let's use the arc sine, because, well, obvious reasons, I guess. Maybe it's not so obvious. But if we use this, that'll work, right? Make sure I'm not crazy here. Arc sine of 5/13 should work? Okay. The cool thing is we put arc sine into a function that has a sine in it, it'll just eliminate the function.
Mm-hmm.
Which is kind of nice. Which is, I think what your point was, right, Cam? You could just use the fact
Yeah.
that it's a triangle. So we end up getting 2k. Well, I don't need to write this all out. Let's just get the answer out of that. That's the last step, right? In fact, I don't know what I'm covering here. Let me just see. I know I have to go really far into the. Oh no, what did I do? Okay, I want to pull this back up. Okay, there we go. All right, so and then I have to pull Discord back up again too. Or else I can't see what's writing. Okay. What do you all get for the answer for this one?
It'd be 4.9 times 10 to the 4th.
I've done this problem before. I don't remember if that sounds right. Anyone else get the same answer? And then we'll write it in vector form like that. Now, this is a problem where we get to kind of understand and learn about a positive and a negative charge, the type of electric fields that they produce. Hopefully, you understand a little bit more about what we mean by the variables that show up in this equation, because this is going to be something that's going to be just used over and over and over again in this class. Not just today, but we're going to keep coming back to it. We're going to say, like, this is the electric field of a point charge, and you need to definitely get comfortable with it. Okay, anyone have any questions? Okay, we got through that problem a little bit faster than I thought we would. These problems are pretty time consuming. And we're going to do another one because I think it helps to reinforce this idea as really this, again, it's kind of one of the fundamental parts of this course is it's a building block. It's a really important building block, understanding the electric field of a point charge, because we can then kind of go beyond that. So let's do a problem that I guess is a little harder. I think it's undoubtedly a little harder. Maybe I should stop just for a second. Did anyone have any questions about this one? Okay. A lot of symmetry in this problem.
Oh.
Go ahead.
Oh, and it may be 10 to the third. Sorry. I may have been off by an order of magnitude.
I'll just go ahead and calculate it because there's not a lot of people answering the chat. Can someone else verify what they got? And if you're sitting there and you're not doing the problem, then
4,900.
You need to kind of start getting involved. The least thing you can do is plug some numbers into a calculator. Yeah, 4,900. I agree. Yeah, 2 to 3. Okay.
Sorry about that.
That's okay. That's my bad I was just trying to keep moving on. Okay, so this is 10 to the third. So is this one. Okay, any other questions at all? Okay, so let's do one that's a little harder. So I pulled this from a different textbook, although your textbook has problems like this too. Doesn't have to be that big, does it? So in this problem, we've got 3 charged particles that are aligned along the x-axis as shown. We want to find the electric fields at the position 2, 0, and at 0, 2. So I'd like for you all to take 5 minutes, try to solve this, and I'll probably have to draw some things for this one while you're doing that. So take 5 minutes, see if you can solve this problem in that time. The first part's kind of trivial, so I'd kind of prefer that you focus on the second part. But if you need to, you should still do the first part. select these all at the same time? Just can't. It's too bad. I can't flip it either. Okay, so some people are actually already getting some answers. Is that enough time? It's at least 5 minutes, right? I think we started at 2:35. Okay. So I tried to mark off some distances here. Didn't do a very good job. I can probably erase this part right here too. So we want to figure out the electric field at 2 different points, and the 2 points we're interested in are basically right here and right up here. So we'll start off with the one that's on the x-axis. Let's move back to the kind of this area over here so we can still read the problem if we want to. Okay, so we need to find the electric field at those 2 points, so we'll just label them. This is the point in the first part, and this is the point in the second part, and the distance out there is going to be 2 meters in that direction, because we're finding the electric field in the first part at 2, 0. Oh, that's part A, so we're doing, this is part A right here. We'll call that one point A. We'll call them point B. 0, wait, XY, right? This is part A, right? Okay, sorry. All right. This is part A. This is part B. That's what I thought. Okay, so first of all, we want to find the electric field. There are 3 different charges here. For each of the positive charges, what direction is the electric field going to point at that location?
To the right.
To the right, yeah. Okay, so this is going to be the electric field, let's say, for particle 3. That'll be the big... we can't... It's not exactly obvious which is going to be the biggest here now, is it? Because 1 is 3 and 1 is 5. This is farther away, so I would guess the electric field for the 5th one is probably smaller, but I can't immediately know. What's the direction for the negative charge going to be?
The left.
Location will be to the left, yep. Because it points towards negative charges. Now this one's really far away, so I would assume it's probably not that big. So we'll draw it as the smallest of these. But before we do it, we don't really know what the answer is. So, okay, we need the electric field for each of those. Let's write this one down here, so we can leave room for this point. So we'll go. We'll just write this all back. For part A, we're going to have the electric field at that point is going to be equal to the sum of the electric field of each of the other ones. So E3 plus E4 plus E5. Okay. In terms of components or whatever, they're all pointing in the same direction, so everything is going to have an only x direction component. So E3 is going to be given by this charge. Look, every single one of these is multiplied by a k, so we're just going to pull that to the outside of this whole thing. So the charge here, just to remind what equation we're using this equation, right? Okay, so k times the charge for 3 is 3 nanocoulombs. So that's, yeah, I'm just going to write 3 nanocoulombs. I know you can convert those in your head or in your calculator. Divide by the distance, so this is 2 meters. So the distance between 3 and here is going to be 1.2 meters, right? So we divide by 1.2. Square that one. E4 is this one. It has a charge of negative 4 nanocoulombs. Now, I did write these as vectors, so what I'm going to have to do here is, I want to be super clear about this. What I can do is, I could just, at the end, I can put an I hat out here, right? And then for E4, I can just write that it's minus 4 nanocoulombs divided by the distance from this one to here, which will be 2.5. And then plus E5. E5 is the distance of 2 meters away. And it's 5 nanocoulombs. And the answer is that 24.24 newtons per coulomb. Do people agree with that?
Yeah.
Get the same thing? Okay, I'm just really quickly just going to check myself because might as well. There's a typo there too. It should be 2 squared in the last term. All of that times 9. Yeah, I agree. This should be in the bottom. 2 squared. There we go. Okay, that part's easy. Let's go on to the second part. I think we want to have a little more room to do this next part. Okay, so now at point B it gets a little harder because every one of these, this distance is 2 meters from here to here. Now for point B, every one of these, except for this one, is going to kind of point off at an angle. So when we add them together, it's just going to get a little bit more work. Okay, so let's do this with actual little arrows here. Let's start with -4 because it's over here. The electric field for that one, what direction does it point? At point B, what direction do I draw my line? Do I go this way? Do I go this way? Up and to the right, down to the left?
Out to the left.
Yeah, we got to point straight down at the charge, basically, right? And, okay. We'll make this one, let's say, like that long. Okay. So that is our, we'll call it E4. All right, what else we got? The electric field for the positive 5 nanocoulomb charge. What direction does that one point?
Directly up.
Directly up. That's right, thanks. Okay. This one is the largest charge, and it's the shortest distance, so this should probably be our biggest vector that we draw, at least here. So let's try to make that one relatively large. That is E5. And then for the 3 nanocoulomb charge, what direction is that point?
Up and to the left.
For this one?
Yeah.
That sounds right to me. Okay, so go away from the charge. Charges, whoops. Why did it do that? Control Z. Doesn't let me Control E. Undo. Okay. Jeez. Okay, that way. And this is the smallest charge, actually. But we need to do some trig on it, so I'm not going to make it too small. Something like that. That's going to be E3. Where am I going to draw the vectors for this one? I think I will draw them, like, over here. So we'll write this label here. And then we'll move this one onto the side. Okay, so we've got the direction of all of these, and we're going to want to kind of write down what they each are, and then combine them all together. That's the best way to start this. So E5 is the easiest, so I guess we just work on the harder ones first. Okay, let's do E3 first. So E3 is going to have 2 components, and the direction that they're going to point is going to be kind of left and up, like this. So let's break it down into components like that. There's going to be one component that goes this way, and then one component that goes up this way. And in order to figure out how we're going to, know what that is, we're going to kind of need an angle. So let's call this angle theta. And then kind of acknowledge that there's another triangle if we kind of go back here. Oh, man. Oh, no, what is it doing? I don't know what it's doing. It's making really strange marks. So if I come down... It's a long line to draw. If I come down this way... Oh, that just looks awful. Okay, let's just draw an actual line. Okay, in that triangle, this theta is the same. So we can figure it out because we've got a 2 and an 8 here. So let's just write down here that theta is going to be equal to the arctan of 2 over 8. Or 2 over 0.8. Could you guys calculate what that is for me? And then while we're at it, we'll go get the other angle that we need. Let's just choose this angle right here. Call it phi. And for phi, I don't think I need to draw this one. It should be pretty easy to see that phi is going to be the arctan of 0.5 over 2. I don't want radians. Okay. So the first one's 68.2 degrees, you're saying? What's the second one? Okay, I'll assume you guys can figure these out for me while I'm doing this. Okay, rest of the things we need to do then is to say, well, this is how I would do it. And personally, I think it's just kind of an easy thing to do. Let's go ahead and also write in here that we're going to have components for E4. One component's going to go that way, and the other component's going to point straight down that way. Okay, so those are our components for those. Okay, so this is how I would write this. So the electric field at point B is going to have an x component that's going to be given by what I'm going to call E3 sub x. What is that? That's this right here. Plus this piece right here, which I'll call E4x. Now both of them point to the left, so basically these are both going to be negative. Okay, but we just need to add them together and then we'll make them a negative. And let's just go ahead and fill out what that is. So the electric field, the x component at point B, is going to be the negative of k times E3. Oh, I should put one more step in here, so I'm not being just completely. So this is going to be E3. The angle theta, to get the x component, we're going to have to multiply by cosine theta. And then we add to that the x component for this one. This is the opposite. Sine. This is going to use sine phi for this one. And then we just plug in our numbers. So it's going to be negative. There's going to be a k. E3 is going to come from the 3 nanocoulomb charge. And now we need the distance between these points right here. Instead of calculating, I'm just going to say that we'll use the Pythagorean theorem, and the denominator down here is going to be 0.8 meters squared plus 2 meters squared. And this gets multiplied by the cosine of the angle. So this is times the cosine of the angle that we got before is 68.2. You guys are saying the second angle is 14 degrees. Is that right? People agree? Okay.
Yeah.
Okay. That's the E3 cosine theta. All of that together there. Plus E4, that was the 4 nanocoulomb charge. I'm just going to keep repeating this. I'm not putting that negative sign in here, right? Because I already took count of that. We already took count of that because we drew the vector to point towards the charge, right? What time is it? Okay. We can finish this up, I think. 4 nanocoulombs, we're multiplying that times the sine of phi. And the sine of phi is the sine of 14. We divide that by something similar, but now it's going to be 0.5. So it's 0.5 squared plus 2 meters squared. And of course, what I'm doing basically is like I'm calling this distance the r, basically, right? And r squared, right, is equal to, at least in the case of the 3 nanocoulomb charge, it's equal to 2 squared plus 0.8 squared, whatever, meters, right? There shouldn't be a decimal at the front there. So hopefully you can figure it. That's why there's no square roots or anything, because it's squared in the denominator, right? So that gives us that whole phrase right there. I saw one person put an answer for this, for the x component. They said they got negative 4.23. Do people agree with that?
Oh no, that was calculating the net. The x should just be negative 2.17.
Okay, because that's a pretty big expression, I will give you all a little bit of time to try to actually solve it out. Oh, stop it. 2.17, you say?
Yes, the negative.
Newtons per coulomb. Negative. Okay, I'm also going to try to calculate this myself. Make sure you're in degrees when you're doing the calculation, too. .21 is what I got. Did I make a mistake? .21. Yeah, I think that's probably the answer. So
Just for Q3?
what I did was I plugged this into my calculator. Now, I'm not going to claim that there's not a possibility that there's an error in what I wrote here. I'm saying that I plugged this in my calculator, and this is what I got for my answer. So check to see that you all can get the same answer. There's a lot of math in these. It's kind of intense how much harder. It's not, like, I don't know if harder is the right word because you're still just doing stuff you've done before, but I think it's hard. I think it's unquestionably that almost any physics problem, it's okay to say that they're hard. What I was going to say is that it's amazing how much harder it gets as soon as you don't have all the symmetry that exists in this problem, right? And that's the main reason I'm doing this, is because your textbook, the one that I encourage you don't worry about buying, University Physics, it has so many examples that are like this one. It has no examples that are like this one, but it has plenty of problems that are like the one we just did. And that's something I really hate about some physics textbooks, is where they give you problems that involve so much symmetry that when you do them, you don't get to see all of the kind of like nitty gritty of what ends up happening when you. Yeah. Okay. It seems like most people are getting this right, or getting the same answer.
Yeah, it is negative 4.2. The x. I thought you were talking about the x component for just one of them, but yes, it is negative 4.21.
If you are keep getting it wrong, keep in mind there is a nano right here, right? That's 10 to the negative 9. Now, personally, when I put it in my calculator, I don't even really worry about that, because the k has a 9 times 10 to the 9 in it. So there's a 10 to the 9, and there's a 10 to the negative 9 in every term. So I just kind of multiply everything by 9. So I just do 3. I guess I could maybe put my calculator up near the screen so I can see. You can see what I typed in. I don't even know how well that's going to come out. Can you see very well what I put on my calculator? I guess you kind of can. Oh,
God,
no.
Your face cam is really small.
Yeah, I don't want it to be too big. I don't want it to obscure anything. So. Okay, what we'll do is on the next calculation, I'll pull up something and I'll show you how I type it in, so that there's no question. Okay, because the next one's actually going to have a third term on it too, right? Okay, so that's just the x component right there. We're not done yet. We need to find the y component. I think what we'll do is we'll just use this space over here. And I'll just shift this off somewhere to the right somewhere. Here, wait, let me make it smaller before I do that. Okay. So now we want to find the y component. So for y, what I would say is there's going to be a y component, E, B, y, and it's going to have an E3y in there. It's going to have an E4y in there. And then it's going to have an E5 in there. So it's going to be equal to E5 plus E3y. And then we subtract this one because it points downwards, minus E4y. I hate what it does to these 4s here. Now, what those are going to be, we'll just write one more line here. We'll have E5 plus E3. For the y component of this, we're going to need to, that's this one. It's opposite, the theta side, so times sine theta. And then plus E4y. Oops, that's minus. Okay. Why did I do that? Thinking about something else as I'm writing. Okay, and then for the E4y, that'll have the cosine of phi right here. And we just need to put all that stuff in. We know our values of our angles, so what we're going to have, I'll actually write this thing in the front up this time, I guess. So there's our k that's going to be multiplied by every term. And then we just need to do q over r squared for every term, right? Because again, just to remind you, it's k, q over r squared. So we've got our k in every term. For E5, the distance between this point and this and the 5 nanocoulomb charge, what's that distance going to be? What's the distance between the 5 nanocoulomb charge and point B?
Just 2.
2 meters, right? And we'll have 2 meters. and we'll square it. For E3, we put 3 nanocoulombs up here. It's multiplied by the sine of theta. Theta was 68.2. I'm sure if we just put 68, it would have been fine. We're dividing that by the distance, which is this thing right here. It's r squared, so it'll be 2 meters squared plus 0.8 meters squared. Plus. The last term is actually minus. So that's minus E4. So that in the numerator is going to have a 4 nanocoulombs times a cosine of 14. Divide that all by the other distance, which is going to be 2 meters squared plus 0.5 meters squared. Like that. And that should give us an answer. Okay, so what we'll do for this is we'll just go to Chrome and we'll use this thing. If there's plenty of online scientific calculators, I just happen to like this one. It's on a website called EEWeb. I don't know, I found this like 10 years ago. I'm sure there's way better ones at this point. I say as it website just doesn't load for some reason. Why is it doing that? Okay. So here. Just get this to where you can actually see it. And then, oh, that's great. Calculator. Oh, OneNote's in full screen, so it's not going to let me do that. Okay, that's fine, it's fine. We'll just go here. Okay, so here's our calculator, and this is the expression we want to plug in, right? This works pretty similarly to a TI. Before I start plugging things in, does everything look right there? Drag this out of the way. Did everyone agree with everything we wrote in there?
Yes.
Okay, let's calculate it. I guess what I'll do is we'll just do 9 times. And what I'm going to do is, like I said, there's a 10 to the 9 here. Nanos 10 to the negative 9, so those basically get rid of, they're all gone in every term. So I'm just going to write 9 times, we'll do 5 divided by 4, that's 2 squared, plus 3 times sine of 68.2. This needs to be in degrees. That's divided by